Okay, in this lecture, let us look at problems with the delta modulator. So there are a few problems with the delta modulator. In fact, there are some serious problems, okay, and difficulties. So primarily, I would say there are two kinds of problems, and they are both slightly contradictory to each other. Okay, one problem would contradict the other one. Okay, so the first problem is called slope overload problem. Okay, and the other is called the granular noise problem. Why it is lagging, I don't know. Granular noise problem. Okay, now let's look at what these problems are and how they are created. Okay, so consider first the slope overload problem. Okay, yeah. Slope overload. So as we have seen the working principle of delta modulator. So in that delta modulator we are approximating a continuous waveform like this with a staircase waveform like this. Okay, so this is my message and this is my staircase approximation, right? Staircase approximation. Okay, this staircase approximation has a basic limitation. Okay, let us see what are the limitations. So due to that limitation only the slope overload problem occurs. Okay, now it can build up at a maximum possible rate, which is governed by two factors. See, you have a signal like this and it goes, this is my sampling interval Ts and this is my step size. Therefore the staircase approximation is limited by two factors. One is step size, the height is called, this is called step size, and let me use this color, and this one is called a sampling interval. Okay, so this is called sampling interval and this one is called a step size. Therefore the staircase approximation is limited by two factors or governed by two factors. One is step size and the other is sampling interval, because there is a limit on the maximum slope you can generate. See, you have a waveform is like this. What is the slope of this signal? This is my Ts and this is my delta, let's say step size. So this is a slope. This is a slope. Okay, and slope you can find out. What is the maximum slope you can get? Maximum slope, which is opposite side by adjacent side. Opposite side is delta, let me call delta naught, maximum slope divided by adjacent side, that is T suffix s. So the maximum value of the slope that you can have in fact is equal to delta naught by Ts, where delta naught is the step size, and the step size will depend on the amplitude of the impulses that are going out, that is the strength of the impulses. Okay, step size depends step size depends on one second, somewhere I lost it. Strength of the impulse. Okay, therefore because the impulses are being integrated to obtain the steps. So if you recall the block diagram of our delta modulator, there we put an integrator, okay, to get the staircase approximations. So the step size will will affect the height of the staircase approximation. So the stronger the impulses, the larger the step. The weaker the impulses, the smaller the steps. Therefore, the strength of the impulse is very, very important. But once you fix the impulse train, that is, the step size is fixed. Okay, once you design the pulse generator with a certain amplitude, then the step size is fixed in that particular delta modulator, and it is going to be constant. So therefore delta naught is constant for a given delta modulator. Okay, it is constant, and that constant is we called delta naught. So the maximum slope that can build up is given by delta naught by Ts. So you have the steps like this, and the maximum slope that one can get is this one. Maximum slope, and this height is delta naught, and this width is Ts. Okay, now let me take one simple example to illustrate this problem very nicely. So let's say this is my message signal, and there is a step increase, or one second, let me draw here. Okay, this is my m of t. My m of t is like this. Let us assume, just for the sake of argument, my signal. Okay, so we can explain this very nicely. Okay, so my message signal has a unit step kind of nature, and obviously at the point of change, this point, there is a change. So at the point of change you have a very large slope. Now what is the slope at this point? Slope you know, right? Change in y-axis by change in x-axis. So what is the change in y-axis? Maybe I'll write down here. Slope is equal to change in y-axis divided by change in x-axis, small change in x-axis, or whatever it is. What is the change in y-axis? Let's say this point is y1 and this is y2. So change in y-axis will be y2 minus y1, and change in x-axis, see, this point is x1 and this point also x1, right? So x1 minus x1. So in the numerator you have some finite value y2 minus y1, in the denominator you have 0. Therefore the slope is infinity. So in this point, what is the slope? Infinity. Okay, very high slope. So you have a very, very large slope. In fact, infinite slope. So your delta modulator, which was approximating this waveform, like this as follows. let me change the color. So it comes like this, compares, so difference is negative, it comes down and again waits, compare this point and this point, then the difference is positive, so it goes up and wait for certain duration and then compare at this point. Okay, maybe let me compare here, comes down because the difference may not be 0, right? Then wait for certain other duration and compare. Now the beauty comes here, and this point and this point are compared. Okay, this point and this point, now the difference is positive, you increase and wait this much duration, and this point and this point compared, again the difference is positive, so positive impulse, right? And then this much duration wait, and this point and this point compared, the difference is positive, so increase positive, you will get positive impulse and wait for a certain duration. Then this point and this point compared, again this is positive, so it keep on goes like this, like that it goes. Okay, so the waveform is coming like this, it comes like this, and suddenly it finds a very large slope. See, very huge slope in this area. Suddenly finds the slope to be too much and cannot track that slope. So because of that, what happens? Your staircase approximation is unable to track this, so it is going like this. So whenever you have a large slope, that slope is not tracked by the approximate value. Okay, it can only go as a staircase, but there is a huge jump. So the maximum possible slope governed by its step size, this step size, and it's a sampling interval. So this is my sampling interval. So eventually it is able to track on the new level. Here it is able to track. Okay, here it is okay, but in this region, no, it is unable to track, and here also not a problem. Okay, so there is a time span over which it is unable to track the waveform because of the slope overload situation. Here, as I said, the slope is infinity, so it is unable to track. And now how do you find the error signal in this? Right, so let me I need to find the error signal for this. One second, let me draw one more time, no problem, so that okay. Suddenly it increases like this, it goes, your sampled value will be, let's say, then it goes up, then again goes up. Why my pen is not writing? Something went wrong. Okay, now let me find the error. Okay, how much error would be there in this staircase approximation? Okay, let me charge my pen for a while. Okay, it goes like this. It is not responding. Why? Oh my god, I don't know what happened in my pen. Something went wrong. Okay, let me stop and continue from this point. Oh, okay, pen is working, but the app is not working. That's a problem. Okay, let me restart this app. Okay, yeah, now it's working. Yes, thank God. Okay, draw. Let me take eraser. Okay, now it goes like this. Keep on shifting like that. Then it increases like this. So what is the error? The error is this much. Okay, so you have this much error you have here. This is my original value. It needs internet connection to work on it. Okay, so here the internet is very poor, so that's why it is giving all this trouble. And this point is approximated value. So what is the error? And this value minus this value. Okay, so just to let us plot the error in this. Okay, so this is the original value and this is the approximate value. Therefore the error is negative, right? So here you have like this, and then positive, and then negative, and then positive, and then it jumps suddenly here in this point. So this much error I have here, this much error. So in this point it suddenly jumps this much height. Okay, and then it comes like this, then comes like this. Okay, and then it keep on oscillates here, and here it goes like this. So this is the error. Okay, so my error signal. So this much error. Okay, so this is the error. So that's why this much height is there here. So this height and this height one and the same. And here this error is shown here like this, and this portion is shown like that. So in this time span you have large error. Eventually it again becomes small in this location. Here small, and here also small, but in this region large. Okay, because there is a finite time span over which there is very large, and that is due to slope overload, because the slope is very high in this region, right? What is the slope in this region? Infinity. Because of that very high slope, this slope overload error is occurred. So you can see that the duration of the error due to this slope overload obviously will depend on these two parameters, step size and the sampling interval. Okay, there are two ways to reduce this. Either you increase the step size, right, or you increase the sampling rate. That means what? Decrease the sampling interval. Okay, so you can overcome this problem. Let me plot like this. What you do is increase the sampling interval, sampling rate. That means reducing the sampling interval. That means, let me write down here, increase step size, and then second point is increase sampling rate. That means what? Increase sampling rate means decrease sampling interval. You take more number of samples for a given duration. So in this case, what happens? See, you come like this. The moment you see the large slope increases, step size like this and go like this. So if you increase this much portion, step size increased, and here also if you increase the step size, then the slope overload distortion will be reduced. Okay, so both the options are available. So this is one method, and in addition to increasing the step size, you can reduce the sampling duration, okay, sampling interval. So instead of taking this much duration, you take very small duration. So what you do is, instead of taking this much, you take here itself, okay, this, okay, reduce the time. Instead of taking this much duration, this is my TS. Now reduce the sampling interval by this amount, a very small amount. Take the sample here itself. Okay. See, originally you have the pulse like this, like that. But what you do, you reduce the sampling interval so that like this, very narrow pulses. Okay, increase the step size, then very small sampling interval, and then again increase, so that you decrease the sampling interval and increase the step size, so that you can avoid the slope overload distortion. Okay, so whenever you have very high slope signal like this, then your staircase approximation keep on goes like this. So it is unable to follow the message signal M of t. Okay, now this is like a unit step signal U of t type. Okay, now we till now we considered a unit step kind of message signal. Now let us look at another kind of message signal, the more standard kind that you normally deal with, that is sinusoidal signal. Let's take a sinusoidal message where a message is let's say M of t is equal to a times sine of 2 pi f t. Let me put 2 pi f suffix 1t. It doesn't matter, where f1 is some appropriate frequency. Now take the derivative of this to get the slope, d times m of t by dt, which is equal to a times 2 pi f1 times sine becomes cos 2 pi f1t. Now what is the maximum slope that one can obtain? D times m of t divided by dt. You take maximum value, and we know that the maximum value of this guy is equal to 1. Therefore the maximum slope is how much? 2 pi a times f1. So that is the maximum slope that one can get from the sinusoidal signal. Okay, so now, so the maximum slope depends on two things here. What are the two things? It depends on the amplitude A, and it also depends on the frequency of the sinusoid. Frequency of the sinusoid f1. For larger frequencies, you will get a larger value of the maximum possible slope for a fixed amplitude. Therefore, if the sinusoidal frequency is more, then the slope also will be more. Therefore, if you want to avoid the slope overload for a sinusoidal signal, what you have to do is make sure that the delta modulator that you design has a combination of step size and sampling interval such that delta by Ts is greater than or equal to 2 pi A times F1. So design a delta modulator such that this slope must be greater than the slope of the signal. Okay, slope overload distortion occurs when the slope of the message signal is larger than the slope of the staircase approximation. To overcome the slope overload distortion, what you need to do is design a slope such that the slope is greater than the slope of the message. Slope of the message signal, that's all. In order to avoid the slope overload condition. Therefore, delta naught divided by Ts, slope of the staircase waveform must be greater than or equal to 2 pi times A times F1. So this is the condition for avoiding slope overload distortion. That's it. So whenever you meet this condition, then the slope overload distortion will be avoided. Okay, so this is the condition that you must satisfy to avoid slope overload distortion problem. So this is the necessary condition so that your staircase waveform m suffix s of t follows whom? The message m of t faithfully when a large step size comes along. Okay, so this is one point that we would like to consider. Okay, and now see, the slope overload distortion problem is avoided by using two conditions. One is increase the amplitude. Where did I write? Okay, increase the step size and then increase the sampling rate or decrease the sampling interval. Now if you do that, then there will be another kind of problem. That problem let us look at. In case if you take a slow variations or small variations signal. I don't have the variations like this, but I have the variation like this, slowly varying signals. In that case, what happens? It goes like this. It keep on oscillates between +1 and -1. It goes like this. Okay, so here 1, -1, 1, -1, 1, -1, and like that. Okay, and you have a large step size, like this is my step size, large step size. So all these variations of the signal are killed because you have, as far as low pass filter output of this will be concerned, it will be more or less like a constant value. In case, see, if you have a waveform like this, if you pass it through a low pass filter, what will you get? You will get a constant line like this, straight line you will get it. Okay, so the capacitor charges and discharges, finally you will get a straight line. The average value you will get at output of the low pass filter. Okay, 0 volt. Let's say this is +1 and -1 volt, and this line will be 0 volt. Similarly, if you give this guy to a low pass filter, instead of getting a slowly varying signal like this, you will get a constant line. Okay, you will get a straight line like this. That slow variations will be killed by the low pass filter. So this is called granular noise. Okay, so this type of distortion is called a granular noise and this is called a granular noise problem. Okay, so you have a kind of noise which is there and it does not represent any kind of variations in the signal. Okay, so whenever you have a slow variation signals, then your let's say you're doing like this, then what will happen? Let me draw this guy like that, then you'll get a straight line. So after the low pass filter, you'll get a constant line like this, straight line. So the slow variations will be killed. Due to the large step size. Okay, and this becomes more serious if your step size is large. Okay, so in order to avoid a slope overload distortion, you need to increase the size. But if you increase the size, then you cannot capture the slowly varying signals. So ideally, it gives some kind of intuitive idea as to what we should do to build a different kinds of delta modulator. Okay, which will have less serious problems of both these problems. Okay, so therefore you need to design a delta modulator such that it should avoid a slope overload distortion as well as this granular noise problem. Okay, one which is therefore it design a delta modulator such that it is able to track fast or rapid changes as well as one which is able to track slower changes or smaller changes. Okay, that's what we would like to I mean, a signal we don't know at what time you will have a small variations or slow variations and at what time you will have rapid variations. Therefore we need to design such that it should adaptively it will change the step size depending upon the signal condition. If the message signal has large slope, then increase the step size, and if the signal is varying very slowly and smaller variations, then reduce the step size. Therefore you need to choose the step size adaptively depending upon the message signal. So the next version of your delta modulator is called adaptive delta modulator. Adaptive delta modulator. Therefore, whenever the signal has large step size, large slope, then increase the step size. If the signal doesn't vary much, then decrease the step size as much as possible. For example, if you have a signal like this, then you keep on increase like that, then you are unable to catch the signal, then increase the step size this much height like this, and then you can follow this guy like that, no problem. Similarly, if you have very small variations, then alternately if it changes, then decrease the step size like this, then you can follow the signal very nicely. Therefore the slope overload distortion and granular noise, both the problems are eliminated by designing by choosing the step size adaptively, and that type of modulator is called adaptive delta modulator. Okay, and that we will discuss in detail in the next class. So let me stop at this point. Thank you very much.